Hello and welcome back. In this video we'll continue talking about standard deviations as a part of section 3.2. So to review from the last video, a sample standard deviation. So deviation is essentially measuring the spread of the data, the variance, the variation within the data. So what we do is we take each data point and we subtract the mean to see how far away are we from the mean, to see how spread apart the data is. After doing so, we square each of these values and sum them all up, dividing by the number of data values in our sample minus 1, and then we take the square root. The population standard deviation is nearly the same. We'll just have to make a few minor adjustments. So first, what we'll do is we'll take the population mean and we'll subtract that from each data value. Remember that x bar is for a sample mean and mu is for the population mean. So that makes sense, replacing that. We again square it and sum all the data values. One big change is that we divide by the number of elements in our population, not the population minus 1. We have to subtract 1 from the sample standard deviation to adjust for S being underestimated often. So we have to divide by a smaller number so that S is slightly larger. And just like this sample standard deviation, we take the square root. So there are some differences, and it's worth remembering that these formulas are different. The variance of a data set is just going to be the square of the standard deviation. So the variance of a sample is just going to be this sample standard deviation squared, and then the variance of a population is just going to be the population standard deviation squared. Notice that we're taking a square root. If you square this, you're essentially just removing the square root sign. The variance we won't use all that often this semester, and it'll mostly be, we'll mostly use the standard deviation. So where does this formula come from? In the formula, this is essentially the main part of the formula. What we're doing is we're taking each data value and we're subtracting the mean from it to see how far away is the data from the mean, how spread apart, what's the variation in the data. This is called the deviation. And we can think that it's just measuring the deviation of a data point from the mean. How unusual is it? If we take the absolute value of the deviation, this is more or less the distance from a value and the mean. So what we could do is essentially, in a abusive language, we could take the average of all of these distances, and by this I mean the mean of all of these distances. And this is one way to measure variation in the data, the spread of the data. However, it doesn't work as nicely as our standard deviation because this uses absolute values. It turns out that in the more theoretical side of things, when you're doing calculations with absolute values, things become a little bit more difficult, and some things are not true in general with absolute values. When we're working with this formula, things are a little bit easier. So I won't go into all the details, but both of these will work in situations. The standard deviation is simply better for our purposes. So I think one thing that will be important to do is to really see what these numbers actually mean in terms of the standard deviation. So the standard deviation is great for normal distributions. Normal distributions have a very nice relationship with the standard deviation. So this isn't a perfectly drawn bell curve, but it'll do. So for a normal distribution, like a bell curve, the very center of the data is going to be the mean. and I'll pretend like this is a sample. So we have our sample mean, and when we are looking at the sample mean, the further away from the mean we get, the fewer and fewer data values there are. Most of the data values will be close to the mean. Now, the question is, well, how many? Can we say exactly how many data values will be close to the mean as opposed to far away? What do I mean by far away? Well, this is where the standard deviation comes in handy. We measure distance from the mean in terms of standard deviation. So how far away from the mean could we be? Well, we could be 1 standard deviation above the mean. We could be 2 standard deviations above the mean, or 3, or even more. On the other side, we could be 1 standard deviation below the mean, as in the mean minus 1 standard deviation. We could look at the mean minus 2 standard deviations, or even the mean minus 3 standard deviations, and so on and so forth. So now that we have these markers set up, I can tell you exactly how many, exactly how much of the data will be between these lines. So for instance, between 1 standard deviation below the mean to 1 standard deviation above the mean, 68% of the data should be between these 2 marks. Between 2 standard deviations below the mean to 2 standard deviations above the mean, 95% of the data will be here. And then furthermore, between 3 standard deviations below the mean up to 3 standard deviations above the mean, 99.5% of the data will be within this region. Okay. So we can say pretty accurately, as long as we have a normal distribution, how much of the data should be close to the mean. Well, within 1 standard deviation, almost 70% of the data should be here. 68% of the data should be within this region. 95, I meant to do that in white, 95% of the data will be between 2 standard deviations of the mean, and almost all the data, all but 0.5% of the data, will be between 3 standard deviations of the mean. And as a rule of thumb, we think of anything within 2 standard deviations from the mean, anything that happens 95% of the time, we consider this common or usual. Anything that happens, anything that occurs beyond here, so something that occurs more than 2 standard deviations above or below the mean, this is considered unusual. And while this isn't very precise, it just gives us some sort of uniform way of saying this particular data value might be an outlier because it's more than 2 standard deviations away from the mean. Let's look at some specific values and let's do some calculations. So the first thing, what we're looking at here is IQs, and they have a mean of 100 with a standard deviation of 15. So we're asked what percentage of people have an IQ between 70 and 130. So what I like to do is draw a little picture. We will have our little bell curve. It's not a perfect bell curve, but it'll do. We have our mean, which will happen right in the middle. And we can start sort of plotting this. So up here, we'll have 130. Down here, we'll have 70. And the question is, how much of the data will be between 70 and 130, as opposed to being below 70 and above 130? Well, we know the standard deviation, which is 15. So I can start going, okay, if we're at 100, 15 above 100 is 115. 15 above that is 130. So 130 is 2 standard deviations away from the mean. Whereas below, if I go 15 below 100, I'm at 85, and 15 below that is 70. So 70 is also 2 standard deviations away from the mean. And using our 60, 95, 99.5 rule, within this region, there will be 95% of the data. So what can we conclude? 95% of people have IQ between 70 and 130. Another way of saying this, 5% of people will have an IQ above 130 or below 70. Now, this is great when things are normally distributed, but when things aren't normally distributed, we can't say quite as much. So what we do is we'll rely on this nice result. So this is Chebychevs Theorem. And this says that the proportion of data, meaning the percent of data, lying within k standard deviations of the mean is at least this number. So this is a number that we can simply calculate. Now, this applies to any data set, not just normal distributions. When it is a normal distribution, we know a little bit more. Bell curves are very nice and are very well understood. If something isn't a normal distribution, if it doesn't satisfy the bell curve, we can still say something. So let's pretend that we don't know IQs have a normal distribution. And all we know is we know that we have the mean, which is 100, and the standard deviation of 15. So let's look at the range between 70 and 130. We said that this is 2 standard deviations above and below the mean. So what can we say? Coming back to our theorem, the proportion of data sets lying within, in this case, 2 standard deviations of the mean is at least 1 divided by 1 over 2 squared. So let's calculate this. So we are within 2 standard deviations of the mean. So 1 minus 1 over 2 squared. This is 1 minus 1/4, which is 3/4. So we can say 75%, and in particular, at least 75% of the data. So at least 75% of people have an IQ between 70 and 130. So this only tells us that at least 75% of people have an IQ between 70 and 130. But we already saw that 95% of people should have an IQ between these because we know that it's normally distributed. But without that extra information, this is all we can say. The very last thing that I'll mention is very brief. The coefficient of variation expresses standard deviation as a percent of the mean. So for instance, for an IQ, we know that the standard deviation is 15 and the mean is 100. So the coefficient of variation is 15%. The standard deviation is 15% of the mean. Whereas heights in the US for males, this is about 4.3%. So male height varies a lot less than IQs.